Swayam Prabha. Digital India. Educated India.
So, if we sketch the root locus now, what do we see? So, let us say this is the real axis, imaginary axis, okay, S plane, okay, 0, and the open loop poles were at -4 and +1. Right. Let us say I use red color to construct the root locus with negative feedback, right. If you recall what happened with negative feedback, the root locus was something like this, right. So, oops, oh, wait a minute, okay. So, I think the point of intersection was at -1.5 and then it broke out and it went in 2 branches, right. This was a k tending to 0, right, and this happened as k tends to infinity, right. This was with negative feedback, right. So, the red line indicates with negative feedback, right. Now, let us look at what happens with positive feedback, right, based on the root locus construction that we did. We can immediately see that with positive feedback, I have one branch which just goes along, which starts from +1 and then it goes along the positive real axis as k tends to infinity, that is it, right. Another branch which just starts at -4 and goes along the negative real axis as k tends to infinity, that is about it, right. So, the green line indicates the root locus with positive feedback, okay. So, of course, I think here the value of k was 6.25, right. So, please check this, I think from the previous example, right, you have to indicate the corresponding points. And what was the value of k at the crossover point? K was 4, right, previously, correct. So, you can immediately observe that once you have positive feedback, what can you say about the stability of the closed loop system? We can immediately see that with positive feedback, okay, the closed loop system is it stable or unstable for all k greater than 0? Is unstable, right, for all k greater than 0. We can immediately observe this, right, because with positive feedback you see that one branch of the root locus that starts from +1 is always in the right of plane, right, no matter what we do with the value of k, right. So, one branch is on the left of plane, but then we need both to be in the left of plane, right, for closed loop stability, correct. So, consequently we have a problem, right. So, that is with positive feedback we are not even able to stabilize the closed loop system with a positive value of k, alright. So, you can immediately see that how the root locus is changed drastically, right, once we change the nature of the feedback that we introduce, okay. But I hope the steps are clear and how we constructed the root locus for this particular case is clear, right, okay. So, now what I want you to do is that I want you to go and repeat the same exercise for the second problem that we did, right. Do you remember what was the open loop transfer function? I think it was k times S plus 10 divided by S squared plus 1, am I correct? Was it the second example that we considered last class? K greater than 0, right? Okay. So, plot the root locus. In the case of positive feedback. Okay. So, that's an exercise. I leave it to your homework. Okay. Once again, notice the differences between what happens when we have negative feedback and positive feedback in this example also, right? That's something which you have to do as an exercise. Is it clear? Okay. Any questions on this?
Sir, if K is less than 0, then just positive.
We are coming there. Good point. You have preemptively gone into the next discussion. That's good. Okay, very good point. So I am going to ask you that question next. But any questions on these steps? I'm sure everything is pretty clear, right? Now we will come to our friend's point, right? What happens when K is negative, right? So see, till now I have been sticking to a case where K is positive, but it need not be, right? Because see, let's say K is a controller gain. See, like in the example that we did last class, right, with the vibrating system. Let's say K we pulled out of the proportional derivative controller, and basically it was a controller gain, right? So now the question is, like it's a real number, right? So it can have both positive and negative values, but till now we have only plotted the root locus only for positive values of the parameter K. What happens when you have negative values? Okay, so that's something which we are going to ask ourselves now, right? So the question that we need to ask is that what happens when K is negative in the case of, let's say first we consider negative feedback. Okay, that's what we are asking ourselves. So this means that G of s h of s can be written as K times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn. But the only change is K is now negative. Okay, so that's what is a change that we have. So then what happens to the closed loop characteristic equation? What happens to the closed loop characteristic equation? Negative feedback, right? With negative feedback, the closed loop characteristic equation is 1 plus G of s h of s equals 0, right? Please remember that. So what happens to this one? If I substitute this structure, it will become as 1 plus K s plus z1 s plus zm divided by s plus p1 s plus pn equals 0. Now what do I do? What I can do is the following, right? I can say let a parameter k hat be defined as minus k. I can do that, all right? So I can essentially define a variable k hat which is the negative of k. So what do you think happens to the range of k hat? So the same closed loop characteristic equation now becomes 1 minus k hat s plus z1 till s plus zm divided by s plus p1 s plus p equals 0, but k hat is now positive. Now the answer is obvious, right? So what do we need to do? we need to follow the steps that we discussed today. See, this looks like a closed loop characteristic equation of a pseudo positive feedback system with a positive parameter k hat. Okay, physically the original system is negative feedback, but this is basically a pseudo positive feedback system with a positive gain k hat. You follow the same steps that we learned today, okay, in the case of positive feedback and positive gain. Okay, you repeat the same step, determine the answers of k hat, then your root locus will be the same. Okay, but then what you need to do is that your answer, whatever answers you give for stability and performance, you multiply by, you change the sign, so that when you quote as in terms of values of k, it should be minus of k hat. That's all you need to do. Okay, when you want to go the other way. Okay, so is it clear? Okay, so now using this, I want you to do the following as homework, right? Repeat, what to say, problem 1 and 2, right? G of s, h of s equals k times, k divided by s plus 4 times s minus 1, of course k being now less than 0, and second problem is g of s, h of s is k times s plus 10 divided by s squared plus 1, k being less than 0, of course with negative feedback, right? Plot the root locus in this case. Okay, is it clear? Steps, once you start doing it, you know, you will become an expert in constructing the steps. You know, as I discussed, just follow the steps methodically, you know, then you will be fine, right? Yeah. Is it clear? Now let me ask you the follow-up question. Okay, well, I think the answer would become obvious to you by now, right? So the follow-up question that I am going to ask is that what happens when k is less than 0 in the case of positive feedback? Right? We can, the answer is pretty obvious, right? If you have positive feedback, what do you think will happen to the closed loop characteristic equation? It will become 1 minus k s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn is equal to 0. So once again we define a k hat which is negative of k, right? So what do you think will happen here? I will get 1 plus k hat s plus z1 all the way till s plus zm and s plus p1 all the way till s plus pn is equal to 0. K hat being now greater than 0. So one can immediately observe that this is like a pseudo negative feedback system with a positive gain k hat. So you repeat the steps with the what to say, odd multiple of pi, right? That condition, right? What we learnt originally. Construct the root locus, find the values of k hat. Then in order to get the values of k, multiply by minus 1. Okay? Is it clear? Okay. So your homework is once again repeat in this case. Okay, so that like you practice all the 4 cases, right? That is, what were the 4 cases? Positive feedback, negative feedback was one attribute, positive k, negative k was one attribute, right? So then you essentially need to use a correct set of steps. Okay, fine. So, if I call the set of steps that we discussed in the previous discussion as the first set, and what we discussed today as a second set, that is let us say we call set 1 as the set of steps with the angle condition involving odd multiples of pi, odd multiples of 180 degrees, and let us say like set 2 is the set of steps with the angle condition involving even multiples of 180 degrees, right. We can immediately construct a grid like this, right. So, let us say we have negative feedback, right, positive feedback. Just to have a bird's eye view, right, of how to what steps to follow to construct the root locus, and then like we have k greater than 0 and k less than 0, right. We can have we can form a grid like this. So, what would be used for the case when we have negative feedback and positive k? Of course, please remember like what is k? We should be in a position to write the open loop transfer function as k times s plus z1 all the way till s plus zm divided by s plus p1 all the way till s plus pn, right. We should be able to basically express the open loop transfer function in this structure, right. Only then we can do all these steps. Okay. So, if we have, let us say, negative feedback and k greater than 0, what do we do? Which set of steps would I use? Set 1, right. Use set 1, right. That is pretty obvious, right. So, then if you have positive feedback and k greater than 0, use set 2, right. That is what we learnt at the beginning of today's class, right. Set 1 was what we learnt till the last class, set 2 was what we learnt today, right, with k greater than 0. Now, then we will discuss k less than 0. If k is less than 0 and we have negative feedback, what did we do? We use set 2, but of course with a k hat definition as minus k, right, that is the difference. And when we have positive feedback with negative k, we use set 1 with an equivalent definition being k hat being defined as negative k. Okay. So, that is how we need to construct. Okay. So, depending on your design choice, like as far as see, sometimes many times what will happen is that we will do a case study tomorrow, okay, like that will essentially run through the entire process. Okay. Now that we have done with root locus design, I will take a physical problem. We will start from the beginning, we will derive a mathematical model, we will get that plant transfer function, then we will try to design controllers, then we will try to find out what ranges of controller gains will stabilize the closed loop system, then how to construct the root locus to satisfy certain performance requirements, right. As we would have already realized, the root locus provides us with a graphical representation, right. So, we can immediately see how easily we can get the ranges of controller gains that would satisfy performance requirements. If you recall, performance requirements were expressed or visualized as an open trapezoid, right, for example, right, in the S plane, left of plane, right. So, with the root locus we can immediately get what values of k, if at all they exist, would place my closed loop poles in the desired region, right. So, things become much easier to visualize and solve, right. So that's something which the entire process I will run through once tomorrow and maybe in the next class, right. So that like we are almost halfway through the course, at this point it's better to pause and take a stock of what we have done and how it can be used for in practical design, right. That's my motivation for doing a case study tomorrow. We'll do a case study, then we will go to, we'll have a brief introduction to state space representation, and then we'll go to frequency response, which should keep us engaged till the rest of the semester. Okay? Yeah. So what we have been doing is broadly what is called as time domain analysis, although like we are analyzing in the frequency domain, but by and large, like the performance specifications that we are putting forth is in the time domain, right, like settling time, rise time, and peak overshoot. That's based on transient response, right, unit step response in the time domain. Okay, so some people will call it as like control design using time domain based specifications, right. We look at equivalent frequency domain based specifications when you do frequency response. Okay, I'll stop here and then like we'll continue tomorrow.